Let's continue with the functions for machine vision in OpenCV. So previously we have covered how we can detect lines and circles and how we can visualize this. So we're going to use the same libraries and the same image. Let's import the standard libraries CV2 and pyplot, and let's read the image. So we're reading an RGB image and let's visualize it. Okay, here we have the image. We can convert it. This is standard so that we can see the proper image, but that's not too important. What I need is now to use another function that is available in OpenCV, and this function is for finding contours on the images. So for this reason I'm going to actually convert this image and use this conversion, which converts the loaded image in BGR to grayscale image. And I'm going to use the threshold function that we have covered previously. The image, and I'm going to binary invert the threshold so that I can get the I and the O to be whitely masked and the white background to be black. If I do a threshold at this value of grayscale, it will select the white color to be white and the darker colors to be black, so I need that to be inverted. And let's check if we have done this properly. Visualize the image. Here it is. I need the visualization with CMap so that it's properly visualized. So this is what I wanted to achieve so far, and now on this image we can apply the find contours function, which returns contours and hierarchy. And I'm going to use several flags here. I'm going to explain them. Find contours is a function. If we provide it with a binary image, it will give us the contours in the image as a set of points, and this is quite useful function when we actually want to get the contours of the image and get those set of points, because then we can use the function which is integrated in OpenCV to match those contours. It's not or to calculate the hue moments of those contours, and for other purposes like convex hull or finding non-convex defects. These are all functions that are actually integrated in OpenCV and that can be used, but this is the most important because we actually can get the contours from this function. So after we have got the contours, I would like to draw them. So I will draw the contours using the function draw contours. I'll use the original image and draw the contours there. This will give us the index of the contours. -1 means all of the contours, and I would like to draw them in, I don't know, since we have blue, let's draw them red. And the width of the line let's display this, the contours that we have found. Okay, just for visualization, I'm going to convert the image into RGB image. Here we have them, so we have drawn the contours. If we print them out, we can see that we have all of the points from the contour as arrays. And we have two contours that were found. So this is the second one starting here, and up until here was the first one. So these are the points here, all of them. But as we can see, for the circles maybe okay, but for this contour here, probably we only need these 4 points in order to calculate that contour. So instead of this approximation none, we can use chain approximation simple. And when we get these points, for the circles we will still get a lot of points, but as we can see, for the rectangle we only get the 4 points of the rectangle. This means that we have done an approximation and we don't get as many points as there are, but we only get those points that are needed to draw the shape. So if we have regular shapes, we can use this chain approximation in order to calculate the contours, but we will get a smaller number of points, which is more optimized than getting all of the points. It always depends on the, so to say, what our application is, on which of these functions we would like to use. So we have the contours here. I'm going to add another image. Let's load this one. And 2 equals load it directly and visualize it. 2, let's see. Yes, here is the star, and I'm going to need it threshold it and invert it. So I get this threshold, and I'm going to use this M2 here. So here it is, and visualize the threshold image. Okay. Okay, here I have a star. Why I needed this? We're going to calculate the contours of this star using the same chain approximation from this image. And now what we're going to do is find the hole. Find the hole. So this will give us the convex hole of the image. So we are getting the contour. That would be the first contour, and what we can also calculate is the defects, convexity defects from the contours and the hole that we have calculated. I'm going to print out the hole. and print the defects just to see the results. There is some problem. Let's check what the hole returns first. Okay, we have the points of the hole, the defects. Should return, we have the contours and we have the hole. Let me check with this. Okay, here is the hole, so the way that they are returned should be a bit different, and here are the defects. So exactly we get the points of the defects. So if we want to, we can actually visualize this. It's a list in list. And I'm going to just copy an existing code for this one that draws lines of the convex hole and the defects. Circle, and we're going to draw them over the image too. And visualize the image. The contours here. Start. I think I'm getting this. It should be the other way around. So it's and here. Okay, here it is. It's just that I didn't convert it to. Yes, it's loaded like this. Let me load it like this, and the threshold would be from converted. To use another grayscale image here, and IM2 just for the. So IM gray is from IM2. Okay, here it is. So now we have it. We have the convex hole which is drawn around it, and we have the convexity defects. This can be used in AAL applications for, let's say, finding the fingertips and finding the internal part of the shape of the hand, or if we want to detect the inner parts, the non-convex parts of a human body in the image after we segment it, and it has a lot of other applications, which is why we have covered it here. So another function that we can use also for from OpenCV is actually the match shapes function, it takes two arrays, so I'm going to take these contours that were calculated for the circle because I have two circles, match shapes, so contours, it was contours, I think the 0 was circle and 1 was circle, and there is the flag 1, 2 or 3 that gives the method. Let's go with 1. It depends how these shapes are compared to each other. So this function actually uses these methods by calculating the moments and then comparing them. I'm going to print the result. So match shapes, I have the contours, another parameter is missing. Here it is, so we have those shapes. If we compare with the second one, it will be a very low number, practically 0. So what I compare here is, the first number was between a circle and this rectangle, and the second number was between the two circles. As we can see, between the two circles the number is very low. If we compare with rectangle, then the number is close to 1 because they are quite different. And this can be used if we have the shapes or the contours of two objects to match those objects and to calculate the similarity. If we have multiple shapes, then we can calculate the similarity between the shapes of the objects using this. Okay. Another function that I would like to cover is the histogram calculation. So again, I'm going to read a color image. With the 3 channels and calculate the histogram of this image. For the histogram calculation, we use the calc histogram from OpenCV. It calculates the histogram of multiple images, so it's receiving arrays. We don't have mask, 256 channels, and so you can find more about calculate histogram in the documentation. It's basically an array of images, the indexes of the images. Do we have masks for those images? And then we define the channels of the histogram. Another function that we can use is not from CV but from NumPy. Here we need to ravel the image, make it like an array, and again specify how many bins are we going to have and what are the range. So we can actually draw the histogram using the pie plot. Of the image, and like this. Let's see what we got as a result. An error. Here. Okay, so here we get the histogram automatically from the image as is drawn, but if we want to draw the histogram from each of the colors, then we can use this code. So we have the colors BGR, we enumerate the colors, and then we calculate the histogram for the image, and we plot those histograms. And here we have all of the colors of the image. As we can see, it's predominantly red. Let me just draw the image also so we can compare it. It's show, and okay, it's a BGR image. I won't convert it. Here it is. It's a predominantly red image for the visualization. Maybe I should. So like this. Here is the image. It's a bit reddish, as you can see. It has a reddish tint, and this explains why for the red channels the colors are quite intensive. And we can see the three-color histogram here. Here is a histogram of the probably grayscale representation of the image. Histograms are calculated in order to get how lit is the picture, how equalized is the histogram. We can also use a equalize histogram function. On the image, this function somehow normalizes the values of the image. So if I use them here on the image, I need to use it for each of the channels. So I'll need to split the image and merge the image, so it will be like this. Let me try it if it works, and then I'll use it. Okay, this will be great. So I have it like this, equalize the histogram, and okay, I equalized the histograms, and here we have a slightly better image than the one that was before. The values here became a bit strange, but nevertheless the image is a bit different. If I comment out this section, we will receive back the red tint of the image. Did I miss the third channel here? Probably. Yes, now it's even better. So try to equalize the histogram. Okay, so this is. There are also some classification algorithms that also use histogram. However, these are not quite often used because color histogram especially, is quite sensitive to lighting variations, and the results that we obtain are not so good. Another function that we're going to cover is not covered in the main OpenCV libraries, but are covered in the OpenCV country Python library, because these algorithms that we're going to cover now are for key point detection and description. There are a lot of algorithms like this, sift, surf, brief, orb, etc. Some of them are free for using, some of them are not free for using. We're going to cover Sift as one of the best and maybe the oldest local descriptors. They can also be used globally. So in the continuation of the video, we are going to actually show how that points of interest are detected, how descriptors are generated for them, how comparison is performed, and how we can use this to detect an object in the image. There are also other operations that can be used, like creating a bag of visual words for image classification and image retrieval, but these are not so efficient, and also there is the usage of these key points for matching of the key points and stitching of multiple images in a panorama image. So first, to create the detector, we're going to create a Sift detector. It's in CV2X features 2D. Sift create, so we detect this. Let me check if it's in the original. Okay, it found it. So let's detect the key points from the image. I'm going to need a grayscale image because this works from channels. For one channel, for 3 channels we need to detect this for each of the channels. So I'm going to have this Lena image loaded as grayscale. Gray image, we have Sift create and key points. This is how we detect the key points. So it's Sift detect the image and a mask if we want to provide a mask. If I print out the KP1, it will give me a set of key points. Each of these key points is an object which contains a lot of attributes, so I'm going to print out some of them. Here we have the point, the coordinates of the point, we have the angle on which the point is showing, we have the size of the point. So these are multi-size points actually, that are counted in the image pyramid, so on different scales. That is why this Sift is actually scale invariant Fisher transform. It lowers down the image so it detects points in different scales, and the response is a response of the function that evaluates how expressive that point is, so that we can actually threshold them. If we want to also compute the descriptors for each of the point, we can use detect and compute, or first use detect and then compute to compute them by providing the points to this one, detect and compute. So it's descriptor 1. Here is the descriptor. It's 128, I think, values which are floating points and give information about the gradients, their direction and their value, their expression. We can also draw the key points on the image, so we can have the gray image. I loaded it like gray. Let me also load it in color and convert it. Here is the image, and I'm going to draw on the image the descriptors. KP1. Here are all of them. There are flags that we can use here for drawing them. These flags are also used when we're drawing the match descriptor that we're going to see later. So these are all of the flags that we can use. I'm going to go with reach key points just to see more precisely those key points. So as we can see, there are smaller ones which are on the regular scale, and as we go up the pyramid there are larger ones. This means that they are on different level of the pyramid or on the different scale, and for each point we can see the gradient, the major direction of the point. This is important because when we are matching the points, after we match them, we can actually see the deviation of the angles of the points, and we can rotate the point by the respective angle and match the points as they should be. So this also gives us some rotation invariance when detecting those points. Next, I'm going to extract part of the image, of the gray image. I'm going to call it gray image 2 and detect and compute the points there just to visualize it, which part of the image it is. Gray image 2, here it is. So this is the image that I'm going to take. I'm going to have this image, it's grayscale, detect the points here and compare them with the points here. So in order to do that, we need a matcher. A common matcher to use, which is not quite optimal, is the brute force matcher. It will try to match all of the descriptors from one image to the descriptors from the second image, and then we can draw the result of the matching. So we are going to draw matches, use this function. It takes the two images, the key points of the images and the matches of the image, and gives a result where it draws the points and draws lines between the points, between the matched points. Here it is. As we can see, we have a lot of matches. We can use default flag if we want to see even the single points that are not matched, but as we can see, there are multiple points that are matched, and sometimes there is not much logic in the points that are being matched. So this is one of the negative sides of the SIF descriptor. We need to do some additional processing in order to extract the good matches. So to do this, we are applying a ratio test. We want the best match, the distance of the best match, to be smaller than 0.75 of the other distance. So if we have matches that are quite close, we are eliminating them. To do this, we are going to use a nearest neighbor matcher, so that for each point on one image we get one nearest neighbor, two nearest neighbors in the next image, not to get all of the matches. And here in the good area, we are going to append all of the good matches, and we are going to present the result by drawing the K and N matches. This is a different function. While we are using the same matcher, but we are using K and N match approach, not each with each, but find the two closest neighbors, and to draw them we are going to draw using this function K and N match. Let's run this. As we can see, we eliminated most of the false matches and we only get the good matches with the image. There are still some exceptions, like this piece of the head here, but there are not many of those. A more optimal matching can be performed using the fast library for approximate nearest neighbors. This is faster matching because we are matching many points with many points. Imagine if we have a lot of images, this will become quite time consuming and complicated. So to do this, we are going to use KD3 approach, and we're going to define a fast library of approximate nearest neighbors matched. We're going to use this KD3 index. The index will use this algorithm and we'll have three trees. In search, we're going to do checks, three checks, or pass an empty dictionary, and then we're going to define the FLANN based matcher. like this, and we can do the matches with the nearest neighbor matcher using this matcher to draw only the good matches. We're going to use draw parameters now. I'm going to copy this code here. So we have a matches mask which is defined. We are enumerating the matches and we are doing the same filtering as above. Here it was 0.75, here it is 0.7, it doesn't matter much. And then we are going to have a match color will be green, single point color will be red to draw the single points and the matches, and we're using the default flag for drawing, and we are going to draw the matches in a resulting image and visualize the image. So here are all of the points detected in the single image, and these are the closest matches that we have found. Now what I'm going to do is perform a transformation on our second image so that we rotated it a little. Here is the rotated image. We can use get rotation matrix by getting the central point of the image first and define this matrix as a rotation along the central point with 45 degrees, and this is the scale, so we can also rescale. I'm using 1 because I don't want rescaling here. And we can use the function warp affine, which rotates the image if we give it a transformation matrix M. We define the width and height of the destination, and since we are using interpolation on some of the points, we are using linear interpolation. So this is the resulting image. Now if I load this image and also detect and compute all of the points and find the good matches, so it's the same code as above, we can actually draw the matches now. Here are the matches, so we have this image and this image here. We have the matches, even though the image is rotated, we can see that the corresponding matches are found. And now we are going to find the transformation function, so we need a minimum number of points that are matched in order to find the transformation functions from one image to the other, and we are going to do this only if we have more images, and we're going to draw the result. I'm copy pasting already finished code. So what we are doing, if we are trying if the good matches here are larger than the minimum match, for finding homography even less point we can use. For the ransack algorithm, I think around 7 was enough. We are converting each point to a floating 32 and reshaping them appropriately. We are getting the matches, we are finding the homography matrix that translates one image to the other, and we are doing a perspective transform on a rectangle because we have a rectangular image where this rectangle should be found in the destination image, and we are drawing that rectangle on top of the image using the polylines function. Let me run this code. So here it is. It found the rectangle at the exact point where this image should have been. If we have multiple images, we can do this transformation. We can also do perspective transformation. It doesn't necessarily need to be a rectangle. It could be some perspective transformation and get the corresponding result. So this is mostly used finding homography transformation using the ransack method, and doing the perspective transform on the image if we want to find the exact place of the object in the image. This is especially important in AAL applications or in robotics applications, and also if we want to perform a panoramic image stitching, we are going to use this finding and matching of key points and finding the homography transformation from one image to the other in order to place both of the images next to each other and stitch them using the exact points. This covers most of the basic and important functions that are used in OpenCV that can be used for various applications like AAL, robotics, and other machine vision tasks, and most of these functions can be used also in other applications, and they can be used as a first part to do some pre-processing, or after some more advanced algorithms like deep learning algorithms to sort out the results and to do some post-processing on them.